Hi there, welcome to this video. So I'm going to go through resting potentials and action potentials, which means how we send signals down neurons. So we're going to start off with resting potential. Now, the key things to remember for a resting potential is it's when there's no electrical impulse. Okay. The next thing to think is that another word for it is polarized. We say that the membrane is polarized. And the charge that we're looking for at resting potential is minus 70 millivolts. Okay, so let's look at how this happens. So first of all, we need to look at the axon of our neuron. And if we say that it's at minus 70 millivolts, what we mean is that the inside of the axon has what we call a potential difference of minus 70 millivolts. That means that in comparison to the outside of the axon, it's more negative in comparison. Now, as we go through talking about resting potentials and action potentials, we only talk about sodium and potassium ions, and both sodium ions and potassium ions are both positive ions. We never talk about negative ions. So it's just that there's more of these positive ions outside and less positive ions on the inside. But the way that we kind of talk about that in terms of potential difference is that the outside is more positive compared to the inside, and the inside is negative compared to the outside. So it's a comparison, but it's actually all made up of positive ions, sodium and potassium ions. So the inside of the axon is negative compared to the outside of the axon, and it has a charge of minus 70 millivolts, which means it has a potential difference across this membrane here of minus 70 millivolts. Okay. Now, the way that we establish a resting potential is we use something called a sodium-potassium pump. So I'm just going to draw my sodium-potassium pump as a circle for now. And the sodium-potassium pump pumps things both ways. Okay, so this sits in the membrane of the axon. So here's my axon just here. Okay, and this purple molecule just here is what we call a sodium-potassium pump. And a way to remember what the sodium-potassium pump does is Nautkin. And that just always reminds me that in resting potential, the sodium and potassium pump pumps sodium ions out of the axon and potassium ions into the axon. So sodium out, potassium in. And that only works when we're talking about resting potential. Okay, so in resting potential, this sodium-potassium pump pumps sodium out and potassium in. It's active transport, so it's going to need ATP to do this. Okay, but what it's going to do is it's going to set up a difference in charge, because as it pumps the sodiums out and the potassiums in, it pumps 3 sodium ions out for every 2 potassium ions that it pumps in. So gradually over time, we're going to get more positive charge because we're getting 3 sodiums every pump compared to the amount of positive charge on the inside, because we're only getting 2 potassiums for every pump. So regardless of whether these pluses represent sodiums or potassiums, we get 3 positive charges pumped out for every 2 pumped in. So over time, we get more positive charge on the outside compared to the inside, and eventually this establishes the resting potential of minus 70 millivolts on the inside of the axon. Okay. Now, we can draw that onto a graph. So there's a very famous graph that summarizes resting potential and action potential. And the first thing that we can label on here is minus 70. So this is labeled the potential difference. So the difference in charge across that membrane. Okay, so that would be 0 just there. And this is measured in millivolts. So at minus 70, we can start to draw our line, and we can say that that line straight across there is our resting potential. Now remember that another word for resting potential was, we can say it's polarized. Okay, and the way that we've established that was using our sodium potassium pump. All right. So what happens when we get some kind of impulse come along and we want to send an impulse down our neuron is we need to establish something called an action potential. Now, another name for the action potential is, we say it's depolarized. Okay, and this is when we want to send an electrical impulse down the neuron. So this is when there is an impulse, and the charge we're looking for is plus 40 millivolts. So we're going to look at our axon again. Now remember that in the resting potential stage, we had this sodium potassium pump pumping 3 sodiums out for every 2 potassiums in. So from that, we're going to establish some concentration gradients. We're going to have a high concentration of sodium outside the membrane and a low concentration of sodium inside the axon. Sorry, outside and inside the axon, not the membrane. And we're also going to establish a concentration gradient where we're going to have a high concentration of potassium in the membrane compared to outside the membrane. So we've set up concentration gradients in the resting potential. So these are concentration gradients that we set up during the resting potential. So what we're going to do now is we're going to make use of this concentration gradient here. So in resting potential, we've established this gradient where we've got a higher concentration of sodium ions on the outside of the axon compared to a lower concentration of sodium ions on the inside of the axon. Now, what happens when, for example, a sensory neuron receives some kind of alert to say we need to send a signal down the neuron? So perhaps a thermoreceptor detected a change in temperature, or receptors in your eyes detected light, or receptors in your ears detected sound, etc. Is the first thing that does is it opens some sodium channels. Okay, so some kind of stimulus from one of your sense organs, receptors, okay, causes sodium channels to open. Now, because we've already set up this concentration gradient where we've got more sodium ions on the outside of the axon compared to on the inside of the axon, these sodium ions are going to diffuse through this channel down their concentration gradient into the axon. Now, at resting potential, this was at minus 70 millivolts. But this minus 70 is going to increase because sodium ions are positive. So it's going to go to minus 69, minus 68, minus 67, minus 66. So this this potential difference here is going to gradually increase. So the potential difference will increase. Now, you've got some more sodium ion channels in this membrane, which are something called voltage-gated sodium channels. So whilst this sodium channel here is open and sodium ions are rushing in to here, we're gradually increasing the voltage. Voltage is another word for potential difference. Okay, so when the voltage reaches a certain threshold, what it's going to do is it's going to open some more sodium channels. So that could be a closed sodium channel, and it's going to open sodium channels. So maybe this one over here that was closed is going to open as well. So when we've got more sodium channels open, we're going to get even more sodium ions rushing in. Okay, so a slight increase in voltage will open more sodium voltage gated channels, and even more sodium ions will diffuse in. Okay, and eventually that -70 in the axon will get enough positive ions in here that it will reach +40 millivolts. And when we reach +40 millivolts, we've reached an action potential. So if we go up to our graph, back up to here, let's see what's going to happen to our line. So it was at -70, and it's going to go up, 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 until it gets to +40. So +40 up here is what we call an action potential. This means that we're going to start sending an impulse. Okay. Another word for action potential, remember, opposite of resting potential, is depolarized. Now, on the journey up there, as this was increasing here, we could say that the membrane is depolarizing. And the way that it depolarized is by opening the sodium channels. So now we need to bring this action potential back down to resting potential. Now it actually always overshoots before settling at resting potential again, but we can label the resting potential here. We can label that that is called polarized. And we can label that that resting potential is established by the sodium-potassium pump. Now this little bit here where it overshot, this little section here, the fancy name for that is hyperpolarized. And as it's coming down here, we can say that it's repolarizing. So let's have a look at how it repolarizes. So if we go back down to here, now you remember just here that we set up 2 concentration gradients. Now we're going to use this one next. So in resting potential, we set up this concentration gradient where we had a higher concentration of potassium ions in the axon compared to outside. So if we want to reduce the potential difference from +40 back down to -70, we need to get some of these positive charges out. And we've got a concentration gradient of potassium ions here, so we need to get those potassium ions back out. So this last section here is called repolarizing. And you remember that in the axon, we've got a concentration gradient where we've got a high concentration of potassium inside and a low concentration of potassium on the outside. Okay, so all we need to do is we need to open, this time, some potassium channels. Now, the potassium channels, very much like the sodium channels, are voltage gated sodium channels. So when it reaches +40, so when the potential difference in the axon across that membrane reaches +40, it's going to close the sodium channels, sodium voltage gated channels, and open the potassium voltage gated channels. So we don't want any more positive charge coming in. We don't want it any more than plus 40, but we need to get these potassium ions out to reduce the charge in here. So it was at plus 40, and gradually we can lose the potassium ions, so getting positive ions out, and we need to get it down to minus 70 millivolts. Okay. So these are voltage gated channels, which means that it's the charge that causes them to open. Okay. So as the charge comes out, the charge is going to go from the plus 40 down, 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 because positive ions are leaving. And in our graph, it's going to come down, 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 and it's going to hyperpolarize, it's going to overshoot, but then it will get back to resting potential again, ready to receive the next action potential when we want to send the next impulse down the neuron. So that brings us to the end of that section. I'll do another one about how the action potential actually travels along the neuron and the speed of action potentials and why they don't go different backwards and things like that.